Good afternoon, everybody, and welcome to this continuation of the seminars after the Easter break. This is the first seminar after that break. First, I would like to announce that next week we are also beginning the IFISC colloquia. We have the first colloquium speaker, López, next Wednesday.
Time is unusual. We don't start as usual at 2:30.
Yeah, we start at 3, but we will provide announcements of that. But it's next Wednesday at 3, the first call. For today, we have a vocal speaker, Rosa, going to give a seminar on recent work in collaboration with an experimental group in Stanford. We call that group. So,
thank you. So today I'm going to talk, as Joren said, about a work that we developed in our stay in Stanford last summer. So we have collaborated with part of these people here. We are there. And it's about coupled conductors and how we can drag some current in a quantum conductor when it's equilibrium, but it's coupled by interactions with another nearby conductor. So before starting with the experiment and the theoretical explanation, I'm going to try to motivate the topic and just to make a kind of summary of some related works that deal with coupled conductors at the quantum level. So first, the outline of the talk is the following. Since the main issue of the work that we have developed is about noise-induced transport, I'm going to just give a brief introduction of that and just to tell you some experiments that have been done. Then I will talk about the Coulomb drag by itself. Later on, all these phenomena is also related with what people call non-equilibrium fluctuation theorems, and what we have studied called nonlinear transport relations. So both things are closely related, and this has been investigated in a couple conductors. And then I will end up with a specific experiment, the Coulomb drag in double quantum dots. We started in 2010 more or less to investigate this type of system in a transport regime that is called sequential tunneling regime. And in this time, we have extended our theoretical model to include some more quantum effects that are called cotunneling tunneling effects. That are able to explain better the experiment. So all the information about the experiment and the theoretical approach are given in this reference. So the first is about the diffusion of particles. So when you have some particles and they are diffused, then you cannot detect any current of particles if you are at equilibrium or you have just thermal noise. Well, all of you know very well, more than me, all these things. But now you can allow to include some diffusion that depends on the state of the system. That could be depends because there is some feedback, there is some noise, etc. So under some conditions, then you can induce even at equilibrium, because of this diffusion that depends on the state of the system, you can induce some current particles. Okay, so then the previous Boltzmann factor, this one is now replaced by some exponential of this new function that depends on the noise or the feedback of the system. Okay, this was also a study in these works. And more specifically, one can consider a potential that is periodic, like this. Okay? Then one can consider as well some diffusion that depends also on Q. We can allow to have the same period, but they are at different phases. They are the phase with each other. They have different phases, and then at the end you can map this system that has this periodic potential and this diffusion factor with a potential that has the periodic potential that we consider at the first time here, and some driving force. So then this system here with a diffusion that depends on the state can be mapped into another problem with some interaction that contains a driving force and a usual diffusion that doesn't depend on the Q state.
But that's,
on the state.
you can only do that in one dimension.
Yes, well, yes. So I assume that is.
So what you are doing is reducing a multiplicative noise problem to an additive one, which can only be done in one variable.
Yeah.
And another
Yeah,
question,
this was
this is classical description.
Sorry?
This is classical description, right?
Yeah, this is classic. It's just to motivate the topic.
Okay.
Just to motivate. That just to say, okay, if I have noise, some feedback mechanism, I'm able to induce at equilibrium conditions and current in my system. Okay. That's the only main point of this. Okay, one can, as Maxi said, find more information just on for one-dimensional system in this work. For instance, classical. Okay, so this has been proved in quantum systems as well. Superlattices, nanowires, quantum point contact, quantum dots. And at the end we can see this like a ratchet effect in which non-equilibrium fluctuations are able, under some conditions, to induce in these devices electrical currents at equilibrium. Okay. So one of the experiments was done in superlattices, in which you have some periodic potential and then you illuminate this superlattice with some light that has also the same periodicity but different phase. And what you get at the end is to induce some temperature dependent, some temperature that depends on the position. Okay. And this electron temperature that depends on the position then is able to drive a current. So this is what is called Seebeck ratchet effect and was detected first in usual superlattices and quite recently in superlattices made by graphene. So also there are some experiments in quantum nanowires in which interactions, you have two nanowires here and there, and then due to the Coulomb interaction you are able to drag some current in one of the nanowires. And you can do that in two different directions, either positive or negative. In this experiment, it is demonstrated that you always drag negative currents, oppose the two nanowires just have currents in the opposite directions when interactions are strong enough. And this is seen here because you can plot what is called the drag resistance, and you can see that this changes the sign, negative or positive, depending on the magnetic field. And at the end, high magnetic fields are able to induce stronger interaction between the two nanowires.
Excuse me, Rosa.
Yes.
When you talk about noise here, you do not mean thermal noise.
No. It's more about the noise, short noise. No, it's not thermal noise. So also you can use this property that noise can induce transport, just to you can exploit this property to build systems in which one of the system is the source of the noise and the other one is the detector. So in this way, your detector is able to characterize the noise of the other system. So you can detect and characterize the noise just by coupling the two conductors. For instance, you can use a quantum point contact, that is this device in which you can pass electrons through these constrictions, and your conductance, that is the current divided by the voltage in the limit of in the linear regime. Then you see these steps, which means that you are the electrons are transversing these constrictions one mode each time. Okay, so then you have here one mode, two modes, etc. So then it's clear that through the quantum point contact you have some current that at the end, due to the Pauli principle, induce a noise, which is the short noise or partition noise, that can be given by this simple expression. For the quantum point contact, you need to, for the quantum point contact, this F is the Fano factor, which take into account the transmission through this constriction that can be unitary or not. So then the quantum point contact generates some noise, and due to this noise, if you couple by electron-electron interaction the two subsystems, the quantum point contact and the quantum dot, then even if the quantum dot is at equilibrium, you are able to promote electrons from the left reservoir to the quantum dot and the quantum dot to the right, which means that you are able to transport charge even if this system is at equilibrium, because the quantum point contact generates some noise.
So
Okay.
where is the quantum dot in that, or where is the detector there?
The detector is,
The
for instance,
quantum
in an experiment that I'm going to show
Okay,
later.
so
The detector is the quantum dot.
The two systems. But
The two systems are coupled. Yes, here I
the
could
quantum point
separately.
contact does not act as a quantum dot. It's not that you look on the transverse direction of the quantum point contact. It's two different systems.
I mean, the two systems are close to each other, and
They are separate.
they are
It's
separate, but they are close.
It's not like looking at the transverse direction
No.
of the quantum. So you
No,
cannot
no.
as a
You
you
go.
cannot use the same for the two things.
So this is, for instance, one of the experiments in which you can. This is a double quantum dot. You can use double quantum dots or single quantum dots, in which your double quantum dot is at equilibrium, and because the double quantum dot is coupled, because it's close to a quantum point contact, the noise of the quantum point contact is able to induce transport through the dot, even if the dot is not biased electrically. So this was already measured in single quantum dots and double quantum dots. In the second case, in the first case, I think. In the first case, the issue was just to try to characterize the noise through the quantum point contact. But the noise was measured directly by the current that is induced in the quantum dot. So by knowing how is the current through the quantum dot, you can figure out how is the noise generated by the source, which is in this case a quantum point dot. Okay, so then there was this theoretical paper in which what is considered is two quantum point contacts that are coupled. The nice thing of this paper is that now one can just, using, for instance, green function Keldy's formulas for non-equilibrium quantum transport, one can write down the drag current through one of the quantum point contacts in terms of the noise of the other quantum point contacts. So here one is the drag circuit and the other one is the dry circuit. So by having some noise in the dry circuit, because you are allowing to pass some current biasing the system, then the drag circuit has a current that depends on the noise of the drive system. Okay. Okay. So in this case, it's clear that the noise-induced transport, because the drag current has in its expression the noise of the drive system. Okay. So then we end up with our experiment. Well, it's not our experiment, it's the experiment of the experimentalist. We have here the system that we have tried to model theoretically, in which we have a top and bottom quantum dots. They are only coupled through interactions, electron-electron interactions, but they are not tunnel coupled. So then we are going to see that by biasing one of the dots, then we are able to measure some current at equilibrium in the other dot. So before this experiment, there was another one in which they used graphene. But at the end, the idea was the same. So by applying a finite bias to one quantum dot, a current is induced in the other unbiased dot. So the only difference is that some of the characteristics that were measured in our experiment are not in this one, because this experiment was more within the sequential tunneling regime. However, in our experiment, there is more coherence, more quantumness. So in that respect, to explain that, we need to add a new ingredient that are the cotunneling processes that I will explain now. So then, as a brief summary, I show you that in coupled conductors, they have interest because we can induce transport due to noise. They can serve as source detector systems in which we can characterize the noise of one of the conductors through the measurements of the current in the other conductor. I will tell you now about the importance of these systems in fluctuation theorems. And also, it's important to know in two conductors that are coupled by interactions, it's important to know the influence of one with respect to the other, because if you want to design nanocircuits, you need to know how they work in the presence of other conductors.
Sorry, I have to recognize that I am lost after the second slide.
Okay, sorry.
So, because if it's too technical, like we can discuss at the end, because I am interested in this nothing. But I understand essentially nothing.
Okay.
The one is, you say, well, I marked one sentence, you say, non-equilibrium fluctuations can induce transport even at equilibrium. Then I don't understand this.
Yeah, so this means that,
self-referring sentence.
for instance, if you have, sorry.
Probably it's a question of what do you mean by equilibrium.
Okay, at equilibrium in one of the systems, not in the global system. So this means that if I induce, I did something wrong. Okay, now. So if I bias this subsystem, this one I'm able to drive a current. Okay. Then this system is at equilibrium.
Well,
no bias is in there.
Well, equilibrium means that you put zero voltage.
Zero voltage, and the conditions to drive a current need some extra energy. I mean, I'm not able to promote electrons from left to right because I need to pay some, for instance, charging energy of this dot. So then, because you have here some current, this induces some noise, some fluctuations, And these fluctuations are able to give this extra energy to the upper system. And then it,
But I would say that the upper system is in equilibrium. If you close it, final charge will build up in one of the extremes, and then they will provide Coulomb repulsion so that finally the current will stop. Or you have open, so you let the charge flow in the upper
Yes,
system.
yes.
It's an open system.
Yeah, they are open system all the time.
So I would say that the system is not in equilibrium.
Well,
but the upper part is unbiased.
The upper part is unbiased, so yeah, maybe we cheat a little bit. Yes. So when I say that it's at equilibrium, this means that this system is unbiased. Zero voltage. Exactly. Yeah. Okay. So I hope now it's going to be more clear. Well, I don't. So then, before entering in the experiment, I'm going to tell you some of the consequences of having systems in which you can induce transport by noise. One of these consequences when you try to investigate what is called the non-equilibrium fluctuation theorems. So here, to start with this part, we need to say something about the full counting statistics, or how we count charge in a conductor, and how this full counting statistics is related with these non-equilibrium fluctuation theorems. And finally, the nonlinear transport relations. So the way to count charges in these systems is, for instance, here you can have a quantum dot and you can have a quantum point contact. So anytime that there is a charge traversing the left to right through the quantum dot, anytime, then the quantum point contact has one signal here. So then if you have some current through this dot, then the quantum point contact is a detector of such current, and then you see some current through the quantum point contact as well. Okay? So in this way you can say that one electron has a pass through this quantum dot, another here, another there, etc. And then you can count the electron through the quantum dot. Okay. So this transport of charge through the quantum dot is indeed a stochastic process, and from here you can also compute the noise, the mean average of the current and the noise, that is the second cumulant. But you can also ask about more cumulants. Then to do that, we need to build this function that is the probability that n.
Excuse me, Rosa. What you call there tau in?
Yes.
Tau, this is not always the same. This is related that it depends on the number of electrons, or? I mean,
Well,
do I understand that each peak is associated with charge?
each peak is associated with charge, but the details I don't really know about this tau in and tau out. I think that they were related more about the tunnel couple, the tunneling rate of the dot for left and right barriers. I think it was related to that, but I don't remember now. But by measuring this profile, then you are able to build this function that tells you about the number of charges that are traversing at some time, t, which is this definition. Okay, so the probability that an electron is transferred through some terminal during time interval. So then experimentally we can access to this function, and then we can build its Fourier transform, the logarithmic of the Fourier transform, which is called the cumulant generating function. By the derivatives of this function, we are able to determine the current, the noise, and the next cumulants.
But I have a very simple question. I mean, for example, in this experiment, current should travel from source to drain, right? What means J1 and J2?
J1 and J2.
Right. I mean, what current we talking about?
Well, I mean, I think they are just the gates that you use to tune the barriers.
But only occur in which case? I mean, because source and drain, you have a contact which is open.
Well, I mean, the only thing that I think we need to know from here is that experimentalists, they are able to count electrons in these devices. That's the only. Okay, so then the experimentalists are able to provide this function, and mathematically we can transform in something that give us the cumulants. Okay. So then, due to what is called local detail balance, one can prove that this function has an internal symmetry that relates, I don't know, maybe, that relates the probability of transporting some charges forward or backward. And they are related with some exponential factor like this. Okay. So then this internal symmetry that is supported by what is called local detail balance then can be translated in the cumulant generating function in this way. Okay, so we can say that this function is the same as this other one when we just add up this affinity. This is the affinity related with the barriers.
This is the last is Pn of minus B.
Yeah, I think it's minus B. Yeah, I think this is a mistake. So then, this is also, this symmetry can be also seen instead from the probability of transferring n charge at time t from the entropy production probability in this way. So this is another way to express what is called the non-equilibrium fluctuation theory, either using the entropy production or directly, if you just consider the entropy production in terms of the affinity multiplied by n, then you get this relation that it was the previous one. Okay. So this is okay if you have local detail balance. However, let me just jump to this. To this type of systems in which this local detail balance is not achieved. Why? Because this is a quantum Hall bar, which is a quantum dot coupled to H states, and this is the same, but considering the spin of the H states. So in these two type of systems, what we show was that when you have magnetic fields, then local detail balance, which is given by this expression here, okay? If you remove this means to have local detail balance, okay? So the transition rate to go forward and backward are related with some exponential factor. This is not fulfilled. And because of this, if you are able to find a system or systems in which this is not fulfilled, then you cannot apply the previous symmetry of the full counting of the cumulant generating function. So that was this one, okay? So this means that there are systems in which there is no local detail balance and this symmetry is not present. systems in which you break time reversal symmetry with a magnetic field, and interactions makes that the response of the system to a magnetic field, positive or negative, are not symmetric. Because these are not symmetric, then you break this local detail balance. Or the system that I'm talking now, the double quantum dot. In this double quantum dot, we can prove that local detail balance is not achieved. Yes.
In the previous formula, the thing getting the invariance was the potential. You have an applied potential.
Yeah.
This is what takes this thing out of equilibrium. It's not a magnetic field. If the voltage is zero, you have a symmetry. Well, you have to reverse time, but also to reverse the direction of the magnetic field, and then there is.
You can reverse.
I mean, you say that the breaking of the time translation invariance because you put an extra driving, or the combination between the magnetic field and the applied electric field. Is this true? At least in the formulas you have shown, this is clear. There is the breaking is proportional to V, to applied the formulas.
This one.
This is proportional.
Yes, I mean,
applied potential.
Yeah, it's the applied potential. I mean, the fact here, the important thing here is that the response of the system to a magnetic field is not symmetric when you have interactions and you are out of equilibrium. I mean, the response is not neither even or odd.
You have
because you have chirality. Exactly. It's because of this. And then local detail balance is not achieved.
No, it was because I don't know what will happen later, but I think that both ingredients are needed.
Yes, both. You need
external applied.
Exactly. You need to be out of equilibrium. Otherwise, this doesn't work. So then, it is clear that, well, in some systems like this with chirality or helicity, we cannot use this property. But even in the absence of such a local detail balance, we are able to write down some relations between what we call transport coefficients. This is a relation that is held always because it's the Green-Kubo formula that applies for linear response regime. And now we are able to find some relations between the noise susceptibilities, that are the noises out of equilibrium, and the conductances, the nonlinear conductances. And also, not only the noise, that is the second cumulant, but also the third cumulant, etc. So people so far have utilized always this symmetry to derive these relationships between the nonlinear transpose coefficients, which means the noise is out of equilibrium, nonlinear conductances, per cumulant, etc. But this is not correct because sometimes there are systems in which local equilibrium is broken. Okay? So then our work in the double quantum dot system was to prove that even in the absence of local equilibrium, we are able to get some relations between, for instance, the noise susceptibility and the first nonlinear conductance, and the cumulant at equilibrium, etc. So you can always write down a kind of non-equilibrium version of the Kubo-Green formula. For instance, here we have the current, which is expanded in powers of the voltage and the noise, and we can also, and then we can use this theorem, this relation that tell us how is the noise susceptibility with respect to the nonlinear conductances. And this is derived even in the absence of this symmetry. which happens in our double quantum dot, because if you think about the double quantum dot and you take, for instance, the drag system, you can write down all the equations of the drag systems by tracing out all the degrees of freedom of the drive system. In that way, then you are not able to get any local detail balance. When you trace out one of the subsystems, then the local detail balance doesn't work, and then you cannot use this symmetry, but at the end, using another symmetry that I have not written here, but are in this reference, then you are able to get some kind of nonlinear transport relation. Okay.
But maybe for understanding this in the context, because the main statement is that in your situation you don't fulfill this relation which we can about two relation.
Yeah, you need.
This is one statement. And then you say, to my understanding simply, then you say, anyway, I can use equation which are fulfilled even in presence of this breaking of symmetry. How is it possible? Simply to understand.
Well, these two symmetries, I mean, you need two extra symmetries, and they are given here. One is quite evident and has is something that is related with the kind of H invariance symmetry of the problem, and the other one is not evident even to interpret physically. Okay? But you can find all the information is here. Okay, so the question is that in some systems you cannot use this fluctuation dissipation theorem out of equilibrium, which is written by this condition. Okay, but people use it. So then you need another symmetries of this function just to derive this nonlinear transport relation. And this is what we have done in different systems, in which local detail balance doesn't hold. So this has been also measured in a quantum dot in a ring, and they, well, more or less measure the relation between the noise susceptibility and the nonlinear conductance. Theoretically, one should have this, but experimentally one has that. And this is much better. This was in presence of a magnetic field, so they plot the symmetric and the antisymmetric combination of the noise susceptibility. Okay. But the important thing here is that experiments have done in order to confirm this type of nonlinear transport relation in quantum dots. So we check also this relation in a double quantum dot that is coupled by interactions, and here we check all of these relations between the noise susceptibilities and the nonlinear conductances in different situations. So even if in this system you don't have local detail balance, you can prove that these relations exist. Even if you are not able to write down a fluctuation dissipation theorem out of equilibrium, you can still have some nonlinear transport relation between the conductances, noises, and next turbulence. Well, this is just about magnetic field, but I am going to jump this because I'm almost, well, I have 10 minutes more or less. So then the next one, the next part of this talk is just about the system itself, the double quantum dot, and the experiment. So our theoretical description is done in terms of a master equation. Before we study already this system, but only allowing sequential tunneling. Here I miss Earth, it's considered. And in a second step, that is the new thing that we have done now, we introduce some cotunneling events to explain the experiments. So this is the system that we investigate at the beginning. And then you can write down with some probabilities, tunnel rates, you can write down the master equation. We consider here, okay. We consider 4 stages for the master equation. The stage where there are no electrons in the system, there is 1 electron on top and no electrons in the bottom. There are 2 electrons, double occupancy, 1 in the top and 1 in the bottom, and 0 electrons. Okay. So to drag current, we need to pass through all these states. Okay. Okay, so with the 4 states and computing these transition rates given by these gamma functions, we are able to get some solution and write the drag current, okay, which has this expression. The important thing is that we can analyze this drag current and we can see that if we go from left to right, we need to pass through all these steps, and from right to left, we need to pass through all the steps, which are just transition jumps from one dot, from one lead to 1 dot, etc. If we compare both, we realize that in order to have a non-zero drag current, we need to have some asymmetry between left and right. And not only that, we need also to have some asymmetry between the transition rates at different energies. So then the transition rate when one of the dots is occupied must be different, even if it is done from the same side, must be different that if this is not occupied. Okay? So then we need that the transition rates be dependent on the states. Otherwise, the drag current is 0. So this is for the sequential tunneling, and if we now plot the drag current when we tune the dot gate potentials for the up or for the top and the bottom dots, so this is the dot level position for the top and this is for the bottom, then we see a spot here which is close to the region in which the charge transverse one of the dot, where the charge changes from n to n plus 1 in one of the dot and n to n plus 1 in the other dot, which is called the triple point. So this is the triple point where transport is allowed. So then we see that having one of the dots unbiased, so here the drag system is unbiased, then we have some drag current because the drive system is biased. Okay, and we see this spot, which is quite symmetric indeed. Also, if we plot the drag current, but instead versus the dot gate potential epsilon 2, we plot against the drive bias, we see that there is a region where there is no current. This region indeed is what is called Coulomb gap. I mean, we need some energy to just start to see some drag. Okay. And this is because
Rosa, one question simply, why you call it triple point? I mean, if you have two dots, then there is only a point of transition from one dot to another. Why it's a triple point? You have other sources to go, or why you call it triple point?
well, it's just to say that just to say that fluctuation of charges always occurs around these positions, and the charge is let's say is fixed in other places. So this is the experiment. In the experiment, well, this is what I said before. Okay. In the experiment, they measure the conductance through one of the dots, the conductance for the other dot, and then they put together the two conductances. So here you see that you can change the charges in one of the dots from m to m plus 1 or n to n plus 1. And the drag current is always higher, close to this triple point, what I call triple point. Okay. So this is our result, including only sequential tunneling, and this is the result in the experiment. In the experiment, they see this spot, quite a symmetric spot, and also they see that here there is some non-zero current, is within the order of picoamperes. And in the sequential regime, when we consider this theoretical model, then we don't see that. Okay? So they measure this drag current by changing also the bias through the drive system, changing the sign of the bias of the drive system, and they see that the drag current still with the same sign. Okay. So this is one of the first experimental facts. The second one is that depending if we plot the drag current through this system, depending on the position of the drag dot, we can be here close to the triple point, what I call triple point, or a bit far away. Then we see that there is a Coulomb gap or not. In the sequential tunneling regime, when we theoretically only include sequential tunneling regime, we always see gap, Coulomb gap. But in the experiment, this depends on the position of the dot level of the drag system. Then why always appears the Coulomb gap in the sequential tunneling? Well, this can be understood because if we allow this type of transition, we need always to pass through this state in which the double dot is doubly occupied, which means that we need to pay some energy, some extra energy that is U. So then we need to provide the system some extra energy U to see some drag current. And this is reflected in this type of gap that we see in the right, in the drag current. Okay? The doubly occupied state is always present there. However, now we allow just to not to pass electron one by one, which is what happens in the sequential tunneling, but also 2 electrons simultaneously. So then, in that case, we are allowing to have cotunneling events, and we can have the same sequence as before, from 0 to 0, but without having this doubly occupied state, because here we can just put 1 electron to the top, and then the top electron can go to the right, and simultaneously 1 electron can go to the bottom dot. Okay, and then we just remove the electron in the bottom. So in this sequence, we are considering cotunneling events, and then the doubly occupied state does not appear. So this means that we don't really need to pay this extra energy. I have to say that all the works that have dealt with this type of systems, they have always considered sequential tunneling. But indeed, the drag current, when you consider sequential or cotunneling current or cotunneling regime, they are they contribute with the same factor, gamma to the 4. So then, at the end, cotunneling event needs to be considered because they contribute at the same order as sequential ones. So, well, to compute the cotunneling rate is a bit complicated because you need to calculate this quantity that involves a lot of integrals, etc. But it's important to know that if you have some initial state and final state and several virtual states, you need to sum all of them coherently. So in this respect, we are allowing more quantumness in our system. So the master equation must be now reformulated in terms of new transition rates that are due to the cotunneling events. Then the drag current looks a bit more complicated. And if we now try to compare with the experiment, we see that the drag current, when we are close to the triple point, looks like this in the experiment, and theoretically it's quite similar. Okay? There is no gap. So then we are able to explain that there is no gap if you include cotunneling events in our system. However, if you move epsilon 2 a bit far away, then you see that the gap reappears again. And we still have the same similar result as the experiment. I must say that our theory, indeed, even if applies for cotunneling events, is only suitable for temperatures that are higher than the tunneling broadening, than gamma. Okay? Whereas the experiment is done in the opposite regime, somehow. Okay. But what the experiment shows is also that, indeed, even if they are able to go down the temperature 5-6 times, the drag current that they obtain is the same, more or less. So they have some kind of saturation with respect to the temperature. So then for that we think that our theory, even if it doesn't really apply to the temperature regime of the experiment, we think that it can be applied. There are things that we cannot explain, and maybe we need a better theory for the cotunneling at lower temperatures. And this is that, okay, in the sequential tunneling we obtain some drag current that is quite symmetric. When we include cotunneling, this asymmetry disappears, as in the experiment. But what we are not able to explain is that here there is some drag current. It's small, but it's there, and we see almost nothing there. Okay, so then maybe we need to go to lower temperatures. So as a summary, well, I have tried to motivate the talk, just telling you about what is the meaning of noise-induced transport. I tell you that quantum dots are relevant devices in this topic. They can use as detector of noise, for instance. These systems are also systems in which some conditions that people assume are not fulfilled to derive fluctuation dissipation theorem out of equilibrium. But even if these conditions are not fulfilled, we are able to recover some nonlinear fluctuation relation between the noises, nonlinear conductances, etc. And at the end, I had shown you that the system that we have studied can be done in the sequential tunneling regime, in which electrons pass one by one, or adding cotunneling events, in which we are allowed to put 2 electrons simultaneously. And these new processes are suitable for explaining most of the experimental facts. Okay, there are some things that cannot be explained, but we think that this is because we need a better theory at lower temperatures. And finally, this is all that I want to tell you.
I think Rosa is a bit in a hurry because of the lecture,
Yeah.
but we probably have 5 minutes
Sí,
for
yes.
questions if there are any. Well, maybe I start. If I understood well, the cotunneling process is one electron jumping in
And the other
at the
one,
same
yes,
time
yes,
another jumping
exactly.
out in the different dots coherently. For this mechanism, for instance, the distance between the dots should be something very sensitive, this process to keep the coherence of the two
Well, yes.
process.
I think so, but
And
in our
if
model,
they are more separated,
yeah, if they are more separated, probably,
this would affect,
yeah,
with respect this cotunneling
yes, but
mechanism.
in our model we don't consider spatial dependence. So, but I guess that yes, because everything depends on the tunneling amplitudes, and the tunneling amplitudes should depend on the spatial configuration of the system. So I guess that this
Well,
should
the
be something.
sequential tunneling probably is not so much
Yeah.
affected.
And also, I mean, for us, this is just a parameter that we put by hand. So.
What is this?
I mean,
The-
simply a comment, simple comment, because what you say that there is no big difference between 20 millikelvin and 2 millikelvin.
Yeah, this is what is
This is
famous.
simply, I think, you should consider how quantum level described in your model, because the quantum level have a large distance between them, then this temperature too small to affect, therefore it not influence this result.
Yeah.
You should think about it. Simply.
Okay. Well,
This
indeed,
is-
in our
This temperature too small. For example, normal quantum dot, we know that the difference is 3 millielectron volt. At this temperature, you should consider is 1.1 millielectron. So it's very small. Therefore, it's not so sensitive to temperature. Therefore, probably you ask an experimental collector measure quantization of level in the quantum dot.
Well, in our theory, we just consider one level.
Yeah,
I
but
guess that in the experiments, the other levels are very far away. I think that they have checked.
okay.
I think so.
Okay, we can thank Rosa.
Okay, thank you.